Start. I'll bring up my presentation first. Yeah, I hope everything is fine. Presentation, camera, audio. Yeah, welcome to our webinar on how to build an on-premise data lakehouse. My name is Vusal. I am co-founder of IOMETE. My background, I'm coming from distributed software engineering, and previously I worked at companies like Uber, Careem, and OLX Group. And this is a nice snowy picture of Amsterdam where I live. And this is a small housekeeping item. If you want to reach out to me, please, you can use this email for your questions. Okay, let's start what I'm going to do. As I mentioned, I will share my experience that I gained at my previous companies and also building IOMETE Data Lakehouse platform over the past 4 years. What is in it for you? If you keep hearing data lake, data lakehouse, data warehouse, and wondering what are they and how they are different from each other, in the end of this webinar, you'll walk away with the clear understanding what are those technologies and what are the distinctions. I think that's a great promise, and let's see if I can deliver that promise to you guys. This is the first part of webinar series, building on-premise data lakehouse. As you can imagine, we cannot fit into just 30 minutes. This webinar will be about covering the concepts and understanding all these technologies, warehouses, Hadoop, data lakehouse. We'll go through the history and understand why do they exist and like what are the industry changes made those technologies to be merged. Once we have a clear understanding why we have these technologies, why we had those changes, and then what brought to us to this architecture that we are telling data lakehouse, then in the next sections we'll go on more like technical levels building that architecture. The end goal of this webinar series not only cover just building on-premise data lakehouse, also to have a comprehensive understanding whole modern data platform, data lakehouse with integration with other systems, data catalog, data quality management, security, ETL stuff, and how it can be used for BI, ML, and AI. Okay, today's agenda. We will start with a brief definition of data lakehouse. Like before we go to all this long journey of the history, like why we ended up this architecture, we want to just like briefly understand what's data lakehouse. Then we'll start our tour over the history and then see what happened over the time, all these changes, and what are the problems made those changes. And in the end, we will have a brief anatomy of data lakehouse, what it looks like, and we'll wrap up and we'll talk about what's coming on the next webinars. So if you leave this webinar, if you forget everything else, it's enough to remember this picture. Data lakehouse is a combination of data warehouse and data lake. If you don't understand data lake, or still you don't understand data lakehouse, what this combination means, don't worry. In the end, those things will be more clear. And this is more like standard definition. A data lakehouse is a unified architecture that combines the best elements of data lakes and data warehouses. I want to talk a technology trend that happens time and time, which is technology evolve, diverge, and then over time get to some maturity level and then converge and simplify. So we will, when we talk about the history, we will see this. We will have new needs that will make the technology diverse into multiple different architectures. Like technologies, Hadoop, data warehouse, data lake, lots of other stuff. And then those technologies reach a maturity level, and then normally we are looking at simplified version. We want to like have all those things in a single architecture, in a single place for better management, maintenance, and also cost efficiency. Yeah, with saying that, let's start our journey or the history, and we will start with the well-known data warehouse technologies. Uh, that is pretty well known or like familiar to us, because that's this system's data warehouses, traditional data warehouses, has a lot of similarities, traditional operational RDBMS systems like MySQL, Postgres, etc. The biggest difference is analytical data warehouse systems are focused analytical queries. It's more like large data sets and more query heavy, and usually tables contains more columns than operational databases. And since the model is different on analytical systems that introduce this well-known concept of ETL, like ETL, because we need to take data from source operational systems or other source systems, and we need to transform that to make it compatible with the analytics models. Data warehouses are good, but then what happened? Like, why do we need to change that? Like, everyone was happy. So let's come to the first change over the history. Like, what were the shortcomings of data warehouses, or what made industries think about a new technology? This Hadoop era started, and it started with the Google's MapReduce paper. Of course, like Google had faced this big data challenges before any other company, because they were already dealing lots of unstructured data, big data volumes. And let's talk about like what are those things that made us to invent this new architecture. Variety of data. So historically, data warehouses, they were really good to process structured data. When I say structured data, you can think about a tabular data, tables, like that type of data. But with the technology, the developments on the technology introduced a new sort of, it wasn't new, it's just we had a demand to work with this unstructured data, like images, audio files, videos, log files, and lots of signals that are coming from IoT devices. And you can and there is a need to manage and like store and process this unstructured data. And as you can imagine, this unstructured data, video files, audio, images, log files, they're generated in a bigger volumes. That's why we need like a new system that's capable of storing a larger volumes of data. And then it was the same time like ML and AI started gaining traction, and companies started investing on that. But with the traditional systems, data scientists, data analysts, they often need access to all the possible organizational data. But with the data warehouses, we had this ETL, extract, transform, and load, and we don't load all the organizational data. We load only a data that we that we get after transformation. But data scientists, ML engineers, they require to find correlations, patterns. They might require to access the raw data. So like in the traditional manner, they have to wait every time when they need a new data, they go to data engineers. Hey, we need this data. They need to go to the source system, implement ETL, and wait that ETL get deployed and that new data to be available. And then they might require another set of data and this loop going on. And this is very slow process. This is that doesn't answer the demands and requirements of this new ML requirements. So speed of data access is important. And cost and scalability, like of course, when you store large amount of data and you need a processing engine that is capable of processing this large amount of data, so you have to be very careful about cost and how you scale that. Speaking about scaling, and this is very correlated with the cost, and there are two main scaling patterns or architectures: vertical scaling and horizontal scaling. And vertical scaling is very well known, and it used to be used a lot in the past with all these traditional databases. They are mostly working on single database. There is a modes that they can use, active standby mode. But yeah, they use vertical scaling. Vertical scaling means you just increase your server's capacity, and there's always a limit. Like you need a more power, but now you buy the most high-end server, but still it's not capable of processing your data. And there is an alternative for that, horizontal scaling. And horizontal scaling is just, you add servers. You don't add capacity to the single server. You just add more machines, more servers. And this is possible with the distributed systems. And Hadoop is a distributed engine that made it possible to go with the horizontal scaling. And horizontal scaling also allowed us to use not only high-end machines, very expensive machines, also like commodity hardware we can easily find. We just add those machines and then get more power. So distributed architecture of Hadoop enabled horizontal scaling, and horizontal scaling allowed us to use commodity hardware instead of very expensive high-end big servers. And that also allowed us to scale process data at scale in a cost-efficient way. So we talked that Hadoop was great. It brought distributed architecture. It allowed us easily store large volumes of data and like process at scale. But what was the problem with Hadoop? Like why we didn't stop there? Why we wanted to build a new architecture? I want to tell one more thing here. If you're paying attention, I mostly talked about unstructured data and semi-structured data. Semi-structured is kind of like not unstructured, but it's not very tabular. It requires more. It requires some processing. But what about structured data? Are we going to use still data warehouses? Unfortunately, these times, yes, because even though you can do processing unstructured data on Hadoop, it wasn't easy, and it was missing lots of stuff, schema management, transactions, all those stuff. So that's why companies ended up having two different systems in their organization: uh, Hadoop for unstructured data, probably some structured processing for larger amount of data, and data warehouses for their gold layer, let's say data marts, etc. So another big problem, one of the biggest problem with Hadoop was like it was coupled storage and compute. Every Hadoop node is responsible for storing data and processing data. In the paper, it doesn't sound scary, but operational engineers know how difficult to maintain scale Hadoop, because not always you have same requirements for your storage and compute, the same scaling requirements. Sometimes you have like larger data, like petabyte, doesn't mean you have to have always 100 servers, because your process, maybe you're only processing last months of data usually. So you have more like storage requirement, but less compute requirement. Since they're coupled, it's less flexible in terms of that scale. So that made a new technology to be emerged, data lakes. And what's the biggest difference between Hadoop and data lake is decoupled storage and compute. By the way, like these technologies are not a completely new technology. It's just improvement with the existing one. So like data lake keep the benefits or best parts of Hadoop. It just solves the problems of the Hadoop, which one is coupled compute and storage, which was solved with decoupling. Another one, Hadoop wasn't very easy to process with to work with the structured data. So data lake brought some improvements on that part as well. So if you look the new architecture, on the right side we see the storage, on the left side we see compute side. So this decoupling also made the industry to invent a new technology specialized on this specific functionality. And especially on the cloud, like we got storage focused distributed storage systems like AWS S3, Google Cloud, Azure Blob Storage. And on the compute end, lots of compute engines are started getting traction. Apache Spark, Apache Presto, Trino, and MonetDB and others. So now we have we have decoupled storage and compute. Like we solved that part. We inherited, like data lakes inherited horizontal and vertical scaling from Hadoop. That's another benefit. But what are the progress with structured data processing? That's the question, like how we can make it easy to work with the structured. Again, like data lakes are improvements on top of Hadoop. That's why it's still good with the unstructured data. So the question is around the structured data. Before like I dive into the structured data processing, I want to explain one concept: storage layouts. So data lakes store data in a file format. And previously in structured files, we had CSV, JSON, but these are plain file formats, and also they're row-based file formats. We need to get new file formats, column-based. But what's row-based file format and column-based file format? Traditional databases, MySQL, Postgres, all the operational databases they store data in row-oriented format. And row-oriented format is good for operational databases, but it's bad for analytical databases. Why is that? Because if you remember from data warehouse post that data analytics are focused on wide column tables. They usually have 100 columns. And row-based architecture stores every row back to back. So imagine you have a table with 100 columns. If you only read, usually in these queries, you use like 2-3 columns from every table in your joins. If you read only 2 columns from this 100 column table, you have to scan all these rows. Even you don't need the data that each row contains. But in column-oriented one, the file formats they store columns back to back, so it knows, okay, this first column starts here and end here, and this like the last column starts here and end here. If I only need to read this 2 column, we can skip the other part of the file, then efficiently only read those 2 columns that we are interested. So CSV, JSON are not good for analytical processing. So new file formats are invented. The most popular ones are Apache Parquet and Apache ORC. The main characteristics of these formats are they are columnar-based file format. They store each column back to back, and not only they also contain some index information like where each column start and end, what type of what are the maximum minimum values of those columns, etc., which helps compute engines to process that files extremely fast. And they're like claims, it's 100 times faster than non-columnar file formats. And data lakes also introduce another concept, ELT. We know ETL, extract, transform, load. Data warehouses didn't have high processing power, so that's why the separate technologies were doing transformation. But there was a little problem with the ETL. With the ETL, transformation is the program part. Like it's easy to introduce a bug there and problem. But if you find the bug a week later, and if you want to fix that, now your source system is not static. It's moving on, even though you fix data, but then you end up with the data loss, or you cannot uh, retransform the same data from the source because source has changed. With the ELT, data lakes provides us vast storage, so we can take data, source data as is, and load into data lake, so we can have a history. Even though source systems are moving, we have a history on the data lake, and then we do transform within data lake, because these data lakes technologies are distributed compute power. They are very powerful to do this transformation within the system. So this new ELT, like Parquet, new file formats emerged, new approaches emerged like ELT, new metadata capabilities added to data lakes, like exposing those files as a format, the table formats. So we work as if we are working with a database. But then we had again a problem. We are not at the same level that we had in data warehouses. Like the working with the structured data is still problematic with the data lakes. The biggest problem is data lakes are insert and query bases. You cannot really do update, delete, merge operations. And also it doesn't support asset transaction, which is very tricky to implement. Like it happened to me in my past companies. Like some companies wanted to, like they tried building scripting, some tooling to mimic updates operations. Let's say with the GDPR, you have to update, you need to remove users' data within your data lake. But implementing that is very tricky because let's say every file are immutable. You have to open file, remove the row, or update the row and write again. Let's say you have 100 files and you are writing, and then you get an error. What you're gonna do, you either have to roll back all your changes or go forward. But another problem is there's no like proper versioning. So like when you are halfway through, some people see the changed records, some people see non-changed files, so they get inconsistent state. Those are big problems. Like if we solve all this with amazing distributed architecture, amazing unstructured processing, with like cost efficiency, and plus if we solve this, then we can have a single system that can do data warehousing and unstructured processing for ML, AI, for everything. And that's data lakehouses are solving. Data lakehouses are adding those improvements on top of data lakes. Again, data lakehouse is not a completely new technology. It's an improvement on top of data lake. So what are those improvements? The main ones are ACID transactions and update, delete, merge operations are supported right now. Another improvement is improved schema and data governance part, because that was really good on data warehouse technologies, but in the data lake, it wasn't there. And there are also lots of other improvements like time travel, versioning of your data, which was very critical for ML operations. And again, all data lakehouse also carry the benefits of Hadoop, which was distributed architecture, processing unstructured data, and decoupled storage and compute from data lakes, and tabular data querying from data lakes. And on top of these improvements, again, I'm coming back to this picture. Right now, like if I wrap up, a data lakehouse now provides a single system for everything, from BI to ML and AI, to store structured data, semi-structured data, and unstructured data, with the extreme cost efficiency, with distributed nature, extreme scalability, and all of that in one place. So what to expect in the next webinars? Like today was an introduction. I just want to draw a good picture. What are those, like some concepts? At this point, I hope I managed to do that. In the next webinar, we will go on building blocks of how to build data lakehouse, like technologies. We see like Iceberg, Apache Hudi, Delta Lake. We see object storage like cloud object storages, on-prem object storage like MinIO, Dell ECS, etc. And like you see image here, Kubernetes. Like I'll describe why this is important in this today's environments, and how to combine this ecosystem with everything else like data governance, BI tools, ETLs, etc. There are lots of topics, concepts that I would love to cover, but unfortunately, due to time, I cannot do that. Data is the new oil. It's valuable, but if you don't refine it, it doesn't have much use. If you read this correctly, and if you're hearing about data products, this is the definition of data product. And yeah, Q&A, and thanks for bearing with me for the last 30 minutes. I didn't have time to check Q&A. I will try to see questions, if there's any questions. Yes, recording will be, and it will be shared after this finish. Yeah, good. Is there any papers you can recommend us reading before the next session? Definitely, I will compile a list of resources that you can read before the next session, so like you would have even better understanding. So that would be, you can make it, that one, very productive. So in any way, I have, let's go back. My email is here. If I find that slide. Yeah, just send your questions, anything that you're interested about, like data lakehouse, even about IOMETE, our company. We have upcoming masterclass about a new way developing Spark ETL pipelines. If you're interested, drop your emails as well. There's only 10 spots left for that. and enjoy your day. Bye.